And Anastasia, do we have the evaluation forms, by the way?
Yeah, let me share it once again here.
In chat, you're putting a chat or?
Yes, in a second.
So Anastasia, I will let you run the logistics. I'm just...
Okay. So we have 3 people today. That's Yuri Sarkisov, Ilya Luchnikov, and Denis Chibakov.
Okay.
Looks like an hour per person. So everybody got the evaluation form? It's in chat. Okay.
Still out of 15 with the same type of criteria. So we're ready.
Yeah, Elena Petrova messaged us.
A few people. Let's wait a little bit.
Yeah, Elena Petrakova messaged us that she's going to be late today because of family issues. She's in the hospital.
Okay. Okay.
Seeing how many?
But we're still missing 2 more, right?
Yes, 2 more.
Okay, there's Michal.
Missing Ibrahim, I think.
Ibrahim, we're just missing Ibrahim for now.
Does anybody know if Ibrahim is gonna join us? Maybe Fernando? No idea. Okay.
Well, let's start.
So let's start with Yuri Sarkisov then, probably. You are welcome to share your screen. And we don't hear.
Can you see the presentation?
Yes, we can.
Just to clarify again, before I start, I have 15 minutes. Is it correct?
What's this?
I have 15 minutes. Is that correct?
Yes. Yes.
Okay, then let me start here. So hello, my name is Sarkisov Yuri. I am the last year PhD student at the engineering system. My thesis proposal, we will discuss it today, and the topic is design, modeling, and control of fully actuated cable suspended aerial manipulator. Presentation contains 2 main blocks. First, we will discuss related questions about the existing solutions. In particular, we will discuss the problem itself, research question, reference model, and relevant areas. And in the second block, we will discuss my approach and hopefully impact it will make on this field. And in the end, I will conclude the presentation. So UAV, unmanned aerial vehicle, already had great impact to our lives. Nevertheless, there are still some applications where they can help us a lot in applications which are dangerous for humans. For example, on the left video, you can see how this climbing man inspects windmill. And on the right video, you can see how these two brave men escape the helicopter in order to inspect high voltage electric power lines. So as you can see, both of these tasks requires one ability, which is interaction with environment. And in order to solve this issue, there are different prototypes developed in the field of aerial manipulation. Let's have a look at them. First, it's this autonomous helicopter with attached robotic arm. It has couple drawbacks. First of all, exploitation of such system is restricted due to the required safety distance between the rotor blades, the diameter of which is 4 meters, and obstacles of the environment at which it operates. Secondly, manipulation workspace is super restricted because of the skids of the helicopter. And lastly, the setup itself is very expensive because middle scale autonomous helicopter costs a lot. Let's consider more lightweight prototype from CNRS LAAS. It's small, it's safe, but unfortunately it cannot carry high weight because it doesn't produce enough thrusts. Moreover, this prototype as well as this one can perform only simple interaction, while more complex task, for example, turning the valve, requires manipulation capability, not just interaction with environment. And to this end, I would like to formulate my research question as follows. How to improve the common aerial manipulator in order to reach a better manipulation performance in terms of robustness, speed, and safety, cost in industrial application, on example of deployment of the mobile robot at the high altitude pipeline. And my hypothesis here is that solution might be decoupling of the robotic arm with aerial carrier by cable suspension with some stabilizing platform, which should provide better manipulation performance in terms of these parameters that I mentioned above. And there are several research sub-questions. They are mostly technical and they're related to how to model, how to control, how to develop, how to design such a system. Yeah, and I would like to define several research objectives. First is to develop, investigate, and test performance of such a system, which relates to the certain requirements which are compliant under industrial conditions. Secondly, to model, simulate, and design control system for certain conditions, technical conditions. Lastly, to compensate for both static and dynamic disturbances by separated actuation systems in some smart, coordinated, centralized way. Lastly, to analyze and compare performance of the received solution with existing one. Okay, my reference model modified from my experience will look like following. I define the key factor as the reachable complexity of the task. So as I mentioned above, there's interaction, and we would like to operate with manipulation capabilities. And this key factor leads to the weight of the aerial manipulator with a payload. So of course, if you want to manipulate, you need a more advanced robotic arm. It's heavier. In this case, you need a bigger aerial vehicle, and in this case, it's become heavier itself. It leads to the size of the aerial manipulator because big and heavier the aerial vehicle requires high thrust, and high thrust requires long blades. And of course, it reduces the safety of environment in the end, which is another key factor here. Secondly, complexity of the task affects required resources for the mission. More complex task requires more resources. And of course, less resources we will use, more customer satisfaction we will reach. Lastly, rich complexity of the task can define a variety of the missions we can perform. And it also leads to the amount of customers as well as the customer satisfaction. And as a success factor here, I would use amount of profit. So as a recommendation from Clement and Nastya, I might replace the less marketing part, but something which we'll call effectiveness of the robot, which is more technical in my case. But in the end, it's about performance, total performance of the system. Okay, let's discuss the relevant areas. My research is on the border of different disciplines. First of all, there's control strategies, which include different model predictive, adaptive, nonlinear control approaches. Secondly, it's a design and development of the systems. Thirdly, it's aerial manipulation itself, because the approach I propose is a type of the aerial manipulator. And lastly, is some connected topics which are similar but not exactly the same. For example, slung load transportation by some aerial vehicle. And let's speak about manipulation a bit. So there's interaction as a general task. And as a part of interaction, we can define manipulation. Manipulation can be fixed base, like industrial robots, or floating base. Floating base manipulation at the Earth environment versus gravity, we call aerial manipulation. And then aerial manipulation, which decouple robotic arm from the aerial vehicle, from the drone platform itself, we will call long reach aerial manipulation. And long reach, it's not only the suspended platform, a suspended arm as shown on the top examples. We can also define as a long reach some articulated drones prototypes as shown on the bottom line. And expected contribution of this work will be following: analysis of the feasibility, exploitation, and functionality of the cable suspended aerial manipulator equipped with 2 actuation systems, propulsion units, and winches. So the video basically shows last year experiments with some draft controllers, but in the end, what we want to reach is this status. So we want to perform some mission which is surrounded by obstacles, by fence, and deploys a mobile robot. And deliverables of my research will be modeling and simulation of the dynamics of this nonlinear, highly redundant system, design and applying of the control laws for this system in order to perform mission robustly and safe way, develop physical prototype, and validate the control approaches at the mission. My research design methodology is different on the different steps on different levels of my research. During research clarification, I use literature analysis and empirical data analysis based on the previous experience of my colleagues. During descriptive study 1, I used modeling, numerical simulation, prototyping, experimental investigation. During prescriptive study, I did some theoretical work, modeling, numerical simulation, prototyping, experimental work, data collection, and analysis. And during descriptive study 2, which is going on right now for me, I do numerical simulation and experimental work as well. So we had this reference model, which is shown right now, and let's have a look at the impact model. So we have our impact, which is this technology, cable suspended aerial manipulator. And of course, it increases the possible complexity of the task. But how will it affect the reference model in the end? So actually, it will modify some links. As you can see, the complexity will not, increasing of complexity will not anymore will not anymore require increasing of required resources for the mission, because instead you will have to just replace the tool, so we can just get rid of the previous one. And as a result, it will increase customer satisfaction. And second one, using the cable suspended aerial manipulator will not require increasing of the size, because actually weight is compensated by the crane or some aerial vehicle like helicopter, which can carry as much as we need without increasing the size of the platform itself. And it will lead to the safety of the environment, and as a result to the customer satisfaction or to the effectiveness of the performance of the system. Okay, regarding research timeline, so there are different skills I had to acquire in order to perform this research. It's a modeling of nonlinear systems and the different types of controllers. It's engineering of high-tech robots and field experiments, which is also takes some efforts. In terms of the time, money, expenses, manufacturing of the platform, crane renting, helicopter renting, flight permission is mostly what we had to pay for. The timeline itself looks like following. So during the first year, I was planning to concentrate on the courses at the Caltech and gain my understanding of the problem itself. So starting the literature review. And the literature review, as you can see, actually is going on during the whole process of the whole 4 years. And because there are some updates every day, researchers don't sleep, they work. So the publication list, publication ability is also distributed during the whole 4 years. Experimental validation is shifted towards the end, but before thesis preparation. And the modeling and control and development is somewhere in the middle. So let me conclude then this presentation. The thesis proposal is aimed at the design and investigation of the novel concept in aerial manipulation field. The research hypothesis has great potential in order to bring an aerial manipulation closer to the industrial applications. Specific objectives and research plan are defined. Reference and impact model for the proposed research topic are designed. So I didn't put any results to be at the same level, but I hope it's enough what I've shown. Thank you for your attention. I'm ready to answer any questions you might have.
Okay. Thank you, Yuri. Any questions from the floor?
May I ask a question? So can you explain, please, what is the key difference between the construction that you offer and the existing constructions?
Can you please specify about existing constructions? What do you mean?
So you are developing a new manipulator, a new UAV manipulator, if I got it right.
Yeah.
So are there any existing constructions of this UAV manipulator?
You mean like this, which are shown on the slide?
Yes. So I'd like you to mention why your construction is better.
I mean, in comparison to what?
In comparison to the existing prototypes.
Okay, the point is that my construction was developed earlier than constructions which are shown here. So basically, these researchers, they cited our work. But I can, in any case, I can distinguish between our work and the existing work. This is lightweight robots which cannot carry high weight and which cannot manipulate with objects. So, for example, the prototype on the left cannot turn the valve. There's like a small single DOF arm link which interacts with the environment. So it cannot perform some advanced task. Like, for example, if you want to perform peg and hold, you have to keep, hold, and insert the peg. And for these cases, sometimes you need manipulation capabilities. On the right side, you see the prototype, which has a rigid link, connected UAV and the arm. So in our case, we have flexible one. It provides a bit different capability and different requirements, but at the same time, it allows us to do more things. For example, we can extend it easily using winch, while this one is just rigid, it has fixed length. Is that answer for your question?
Yes,
Or
thank you. No, I got it.
okay.
Can you show, the reference model, Yuri?
Yeah, sure.
You see, what I find in your reference model is that, okay, you have the weight, measurable, size. What do you mean by the size of AM is
Aerial manipulator.
the task? What's that?
AM stands for aerial manipulator.
Okay, size. What do you mean by
Size. So actually it's specified right below the figure. You can see that I meant the blade's length. So as I mentioned in the beginning of the presentation.
blade length? Blade.
Sorry?
How do you measure the blade length?
By diameter. For example, let me
But you
come
have
back.
blades.
For example, at this helicopter at the
Yeah.
left top corner, I can measure the diameter of the blades, and it's super long. It's like 4 meters.
Yeah.
And because of that, the size of this aerial manipulator is super huge, and it's not applicable in industry because it requires some distance between the UAV and the operational point.
Okay, you see that as a negative. Go back to your reference model.
Actually, it's not just my view, it's a view from industry. It's something that we get as a feedback.
And how do you, my comment on your thing is that it seems to me too high level.
Too high level.
Yeah, too high level. You
Okay.
don't mention, if you take at your objective, what is your real, I think I'm going back to the question of Dennis. I think you're
Okay.
hiding your real objective.
I'm hiding it.
Yes. I think you have a very precise objective. I don't know, I would see. I think that you're looking, and you say it in your, when you talk, is that it's a matter of maximum weight or load that you can carry. And the weight of AM with payload, I don't think that's important. I think for you, what's important is what can you do? What Dennis is saying too is how much, if you have to turn a valve that's got so much resistance, this is a key factor. Is that not what you want to maximize the capability of the remote manipulator? Is that not your goal? You want to maximize the capability?
Yes, and actually it's defined as a key factor. So reachable complexity of the task.
But then to me, the reachable, it could be very light. It could be a feather of a bird. I'm reaching, okay? And I need a complex tag. I need to put this feather in some place. But this is not what you're doing. It would seem to me, yeah, you're doing this type of thing, but you are working with significant load, significant power, right? Is that not what you want to do?
Not only this, I want to work with significant load and significant power in a safe way, in a safe manner.
Okay, well, it should be there. Then we should see in your reference diagram power, maximum weight, and not the weight of the AM. To me, the weight of the AM, yeah, okay.
With
but
payload.
Right?
Sorry?
The weight of the area manipulator is not what you want to optimize. To come back to Dennis' question, is what your real objective?
So actually, it's exactly what I would like to optimize, because higher payload, higher weight. I mean, the payload with a high weight requires weight of the aerial manipulator with a higher weight. increasing the weight of the payload, we should increasing the weight of the aerial manipulator.
But then is that, if you put a crane, in your case, you put a big crane,
Yeah,
how do you calculate the weight of the AM? Because I could have a huge AM area, so I have a crane, right? So I
yes,
calculate the whole boom and the whole truck and the whole crane.
exactly.
plus what I add, right?
Yeah,
But is that really important?
that's the point that in this setup, the crane holds the weight, not the aerial manipulator holds the weight, but the crane itself.
But why did you decide to go with, I don't know if it's you who decided to go with the crane, but what's your objective?
Research objective or objective in general?
Well, I think the same, well, I guess they should be close.
Okay, to improve common aerial manipulator, which are basically independent, which are basically UAV with attached robotic arm, in such a way that we can apply them to some, not to some, to the specific industrial tasks. That's the objective.
But then why use a crane?
Because all,
Going back to Dennis had a very good question for you. I think that this is because you're not, to me, I would say that the size of the EM, the weight of the EM are not critical factors for you. What your really critical factor is the payload and how far you can work with this payload and how much you can twist or affect the capacity of the manipulator to do meaningful tasks, isn't it? That your goal? That's what I see with your research.
But it's here. The capacity of the manipulation, it's the reachable complexity of the task, and the payload is in the weight of the aerial manipulator with the payload. We use the crane only because of the one simple reason. All industrial constructions that we would like to work with are built with the cranes. So essentially, crane can reach them. We don't want to fly far away. We don't need to, because crane can reach every industrial site.
I understand this, but you see, it's not the variety of missions. To me, you're attacking a very specific problem, Yuri. I'm just trying to better understand what understand what you're trying to do. Is that, and I think it's a great goal. I agree. It's just to me, I think you can present it in a much more effective manner. I would think is that I think that the reason why you take all those steps is because you want to do meaningful tasks, and the reachable complexity of the task. I don't know how to measure this. Tell me how you will measure reachable complexity.
Yeah, so I would say there's at the super high level, we can define interaction and manipulation. So interaction is a low complexity and manipulation is a high complexity task.
But how can you measure this? What units? Always ask yourself, what are the units?
I mean, there are not like 1, 2, 3 units, but there's kind of low, middle, high level tasks. High complexity.
How do you define them? Do they have a
degrees of freedom somehow? Maybe you can formulate.
No, I mean, I would say it's just a matter of the field. For example, peg and hold is advanced task for everyone in the manipulation robotics, while just pushing someone is something low level, low complexity. It's just in the robotics manipulation, at least it's a case, but there is no kind of scale official one. It's just if you present your research and you perform the peg and hold, and it's kind of high level research.
But okay, fine, but what? Okay, let's go on to is how you see your success factor is amount of profit.
As I mentioned, I was advised to replace this part by something more engineering, more technical. So I thought to replace this 3 blocks: customer satisfaction, amount of customers, amount of profit, by effectiveness of the robot, applicability of the robot, performance of the robot.
Yeah, Effectiveness. What do your units are very complex. What's effectiveness? How will you measure effectiveness?
So it's very, as you mentioned, it's something very complex. So there are different criteria. I mean, in terms of the efforts, like deployment efforts, safety, money. I mean, a lot of units will be inside of this effectiveness. But mainly effectiveness in the application, in the applied case for the real mission.
Okay, now I see. Okay, so you're gonna have a table in your thesis. The goal is to define clearly effectiveness.
No. I don't define effectiveness. Yeah.
You don't define effectiveness?
I mean, officially, how can I? Because it's super complex. It will require comparing of the different types of systems. I mean, it's.
But then I'm coming back again. Dennis is asking you, what are you offering better than anybody else?
Okay, so the new approach, suspended aerial manipulator, first of all. Secondly, I mean, and which leads to the certain benefits. Secondly, as you can see from the impact model, which basically what I offer with my system was this approach, is a higher effectiveness in terms of the required resources and in terms of the size of the aerial manipulation, which are a measurable success factor for me. I will open my impact diagram one more time just to show it. So I replaced those links with a new one for this measurable success factor.
Okay, but
So
work to simplify your effectiveness. If you say, oh, that's too complex, that means you cannot have it as a success factor. If you say it's too complex to measure, then it's, I think that's what I say. I think you keep your reference model and your impact model at too high level. That would be my suggestion to you. Bring it down, because I'm sure in your thesis, in the papers, you will certainly talk about torque. You will talk about reach in terms of, you see, it's reachable. So there'll be a distance somewhere, distance from or there will be the maximum load that you can apply on a building, on your application.
Okay.
This is
Yes.
trying to reach, right? Is that not what you're trying to
That's correct. That's true. But in this case, all these models will be super huge.
What would be super huge?
The models, reference and impact model, there will be a lot of many links, many attributes, many blocks, many elements, much more than now.
I'm not sure. I think if you focus on what is very specific and direct, I don't think you would have that many. That would be my perspective. But I will let other people ask questions now.
I mean, I will try what you proposed, but I would just small comment from my side, because we considered only one reference and impact model on the Ivan example. And in my opinion, then it's kind of high level. So that's why we tried, maybe, at least I tried to do something at the same level. Maybe then.
But Ivan brought the measurable success factor very concrete. If you look at it, he can measure his success factor easily.
I can also size of aerial manipulator and required resources. I can measure it. In my case, those two are success measurable factors.
Which one? What do you call success? Which one success?
I will show you reference model again. So they are in the green circles. It's the size of aerial manipulator, which basically is the blades length, and the required resources for the mission, which includes time, money, license, equipment, maintenance, and amount of people.
Okay.
Those are two measurable success factors which define this effectiveness of the robot, which at least I measure in the scope of my research.
Okay. But because I was looking at the measurable success factor, you say required resources for mission and size of, okay, so you say the more concentrated you are, the better it is.
What do you mean more concentrated?
If the size, you say if the size of the blade, the safety goes down. So to increase safety, you need to bring it much closer to the
Exactly.
collar,
To the
right?
to the manipulation point. Exactly.
Okay, good. All right. But I think it's, and maybe one last comment, Jurit, I think it's a variety of missions that maybe you can define in terms of maximum reach or maximum load, or I think this is one of your big objectives.
Yeah.
No doubt about it. And I think that this is your, for Dennis there, I think that this is the real answer is in the variety of mission, but you need to quantify it into a few clear variables.
I can do it, but the point is that I don't really analyze it, because in my case, I analyze the performance only on the one mission, which is deployment of the mobile robot as a pipe. So theoretically, yes, I can analyze this variety of missions, but in scope of my research, I'm not going to validate on this variety.
So you're not doing any meaningful task with your manipulator?
I do meaningful task, but only one specific. But I mean, in the lab, yes, I do many of them. But in the similar to industrial scenario, I do only one, because scenario itself takes some preparation.
Yeah, but then you could quantify that one or the ones in the lab as your, I'm sure you have 2 or 3 or 4 variables, parameters.
Okay. Yes, I can do that.
You have 3 or 4 critical parameters. And if you had those parameters, this would have been satisfied very quickly. And myself too, you see?
Okay, yeah.
I think this is what you're missing. And then effectiveness will be defined by these parameters. You see?
Yep,
I have
thank
a
you.
comment quite aligned with what Professor was talking about. If you can more clearly specify which tasks are getting possible to be solved with your system, which are not possible to be solved with others from technical point of view, which technical parameters of those systems do you influence with your solution? And to make it more specific, also just looking at your reference model, customer satisfaction, for example. Okay, I understand that you tested with one specific application with the mobile installation or something. So maybe specify it here because it's not any customer you're going to satisfy. It's just this particular group of tasks. And that's fine, but mention which aspect exactly of which interest customer are you going to satisfy. Otherwise, it's getting like, yeah, really too high level, like satisfaction, amount of customers. You're not solving all of the all of the problems of all.
Yes, certainly.
Okay.
Thank you. Thank you.
Any other questions from the group?
Yeah, I did all the questions. I'm sure you have questions. Nope.
So can you get back to objective slides, please? Slide.
Yeah, I reduced them based on your comment. Thank you. Yeah.
I'm not absolutely sure if I'm right, but yet looking at the
Mhm.
third objective, then you state, then you formulate it in a way to compensate by separated actuation systems coordinated by a centralized control framework. It makes me wonder if it is too narrowed down to solution once again. So
Mhm.
as far as I see, it's better in research questions and even in objectives to stay more open, not specify how exactly are you going to solve the task. But if professor had other comments, go for it.
Well, I don't know. I was thinking while you were talking, my thing there, what you have is very, very interesting on this disturbances, by the way, Yuri. And I think that you could change, I would suggest that you change your safety by a criteria quantifiable directly with the disturbances. In safety, I would, I maybe have or you replace it, or you have another one, but it's accommodation of disturbances, and it's very, very important. I agree with you. Very, very important.
Mhm.
You see, this is what I mean by being more specific.
Yeah,
Then
got it.
you have very nice, in the objective there, you have very nice quantifiable factors. Of course, you cannot put all of those in the reference on the impact model, but you have some content there. Very interesting. Okay. And go back to your research question.
Sorry, I have a question in the slide. Can I ask it first?
Yeah. Oh, yes, go ahead.
Okay, so you specify that the wind speed in a windy day is less than 5 meters per second for this test. I understand that this for like performance comparison, right?
I'm super sorry. Can you repeat
Yeah.
the question?
And point number 4.
Yeah.
You specify for comparison of the performance in a windy
Yeah.
day with
Yeah.
wind speed is less than 5 meters per second. Don't you think that the wind speed for the test is very low, considering that it's a crane or it's very high? Like at high altitudes, wind speeds of 5 meters per second are very low.
Okay, I would reply honest. I just put a number. It's not like a real requirement, because in the end we have to tackle the all wind, any wind.
Thank you.
But
Okay.
you didn't do any test on the wind, right?
I tested already at a very strong storm close wind. It's fine, but I cannot really measure it. I don't know how fast it is.
Well, if you go, yeah, okay. But you probably could get some order of magnitude of the wind. If it was a storm type,
I will, from the weather forecast, I will, but it's not here at the slide.
okay, good point, Ibrahim, good point. All right, go to your research question. You see, it's the term manipulation performance in terms of robustness, speed, safety, cost, and industrial application. Industrial application, it's the variety, okay? But safety, you have it, cost, yeah, so the setup cost and so on is important. You kind of have it. Robustness, you don't have it anywhere.
Mm-hmm.
So anyway, it's how to improve the common aerial What's a common aerial manipulator?
It's what was shown before. I presented first. I started with a presentation of some existing solutions for the problem I defined. And these solutions I call the common aerial manipulator because they already exist and they're quite common in the field. Because as a rule, when you speak about aerial manipulation, the people think about the drone with something attached.
Oh, I see. So these are the ones, not the people doing the inspection for washing windows or wind turbine.
No.
Not
I meant this one, which are here.
Yeah, okay. They're not so common. That's what I would say. I would say how to improve aerial manipulators, because common, I don't think there's any common yet. They're too new, I would say.
No, 10 years old at least.
Yeah. Okay, good. Thank you.
I have a question. Uh, like, I would really like to know like real application of such concept. Maybe there are like one or two applications that are really neat, like such concept.
Yeah, sure. I mean, why you didn't like
Yeah,
those one, for example,
okay.
which are presented here, like inspection of the blades of the windmill, or operation of the, I believe these guys at the right video, they replaced some, I mean, there is long video, like 10 minutes, but then they replaced something at this power cables at the station and same. So they took something and they put something new. I don't know what was that, some detail, but for example, something like that. Or operations of hazardous, dangerous conditions, Fukushima and so on. Not only cleaning, but
That's why,
Yes, I mean,
yes,
there
go ahead.
are like there are drones without
Mhm.
helicopter. As we said, they are sometimes they're not super effective and they need like more power and they can like die very fast and that's like something like that. But maybe like I just didn't think about like where you can implement like such concept where you need a robotic arm and also you need like long time operation. Yeah, well, maybe yeah, such examples are good. Yeah, just wanted to clarify.
when you need robotic arm, and okay, so you not satisfied with those applications, you want something
No, I'm
different.
satisfied with this, but just I don't know. Currently, I'm also reading about implementation of UAVs, and
Mhm.
yeah, there are so many like applications, but I thought that it is enough power like now to make such a job, and like it is not required like people like pilot as a human, and
Mhm.
yeah, because like I just didn't think about such concepts. Yeah, your examples are good, but
It's fine.
yeah.
Okay, I will give you one more. We actually, this mission I showed you, it's inspired from the real task. So we operated with, we communicated with the refinery. Okay, for Russian speakers, it's like нефтеперерабатывающий завод. And the problem was that they had a lot of pipes at really high altitude, and they wanted to inspect them, but inspection not always from the top, but sometimes from the bottom of the pipe. To this end, they wanted to have a mobile robot, real robotica, real robot, which basically rides through this pipe, along the pipe, around the pipe, and so on. But in order to deploy it, for example, here you can see such a robot. You have to, I mean,
That's okay.
you have to press this deployment cage, or I mean, if there will be different deployment type styles, and maybe there will be different tasks. But in this case, there is a cage, and in order to safely deploy the robot, which has magnetic wheels, you have to really push the cage towards pipe, else the robot will not go away.
Mm-hmm.
So you see that we push with this hook the cage towards the pipe, and only then robot can go out safely without any issues.
Yes, I see.
In this case, you have to really hold and keep the specific tension. So there is like force torque sensor and then the effector of the arm. So you press it with a specific force and you hold it while the robot not fully leave this cage.
Yuri, can I ask you maybe, sorry, Katerina, Are there some patents involved in this?
Oh, yeah, don't record this. Don't record this. No, I mean, we submitted the patent for the system.
Question I'm asking is because I've seen, and it's good for, it's a comment for all of you, is that I've seen some PhD thesis because there are some industrial applications or commercial in this case, which makes the description very hard because you cannot say everything. And that's why I'm asking Yuri if he's in this mode, because you have a difficulty to say it. So maybe there are some things that you don't want to say. It could be, or you feel totally free. You see, that's depend, because I've seen some thesis really restrictive on this, and it makes the poor guy or the poor girl that defends it in a very difficult position, and the jury members also. All right.
I
So
don't have any restrictions except some specific hardware, very detailed hardware description of the system. So I cannot describe this, but
okay,
else it's open.
okay, good. Thank you. Anything else? Good. Thank you very much, Yuri.
Thank you.
All right, so we'll take a 5-minute break and we'll go into the next one. The next one is going to be Ilya. Is that Ilya, Anastasia? Who's next?
Yes, supposed to be you.
Okay, Ilya. So 5 minutes, Ilya, will start. All right, so we're ready. Our 5 minutes is over. And I think Ilya must be ready by now for sure.
Can you see my screen?
Yes, we can now.
With presentation, I have two screens actually. Or with something else. With presentation.
No, we see, we see your presentation, PowerPoint, I think, or something that looks like it.
Okay.
Yeah.
Okay, so let me start. Hello, everyone. Today I'll be talking about my research proposal, that is numerical methods for model identification optimization quantum technologies. And yes, I haven't done yet the impact model because I didn't have enough time. So I hope that I'll do it in the written proposal by the end of this month. So let me start from the reference model. As I said last time, being able to manufacture high quality quantum devices opens a lot of new advantages in, for example, in development of new types of precise measurement devices, new methods for material simulation, new methods for some currently intractable applied mathematics problems, and for development of new types of secure communication lines. However, quality of quantum devices highly depends on quality of hardware solutions, mostly depends on quality of hardware solutions. While quality of hardware solutions depends on various factors, including some applied mathematics methods, such as control methods, model identification methods, design methods, and in general, optimization methods, constraint optimization methods. So here I, by the red color, I marked key factors. And these key factors depends on measurable success factors that for optimization methods here are scalability of optimization methods, efficiency of optimization methods in practice, mathematical guarantees of convergence, and probably the most important is universality, because optimization problems in quantum technologies are very different, and it is very difficult to develop a precise optimization technique for each particular problem. And additional measurable success factor for model identification methods is interpretability. That means that a model identification method shouldn't be just a black box. It should be a physical model that can be understood by a scientist, by a physicist. So based on the reference model, I introduced my research question, that is, how can one develop a unified numerical tool for model identification, control, and design in quantum technologies? So I split this task. I divided this task, this project, into two parts. Each part is dedicated to two key factors. First factor is optimization methods with quantum constraint, performance optimization methods with quantum constraints. Second key factor is quality of model identification methods. So my goal is to improve both parts, optimization and model identification methods. So and I'd like to start from the methodology and from hypothesis for the first part of my project. So let's say that we have a mathematical optimization problem. Here, let's say that we want to minimize some function that is represented by level curves. So a function takes constant value on a curve. However, we are forbidden to violate some set of constraints that here represented by a blue curve. And at this step, I need to introduce a hypothesis that typical constraints in quantum mechanics and quantum technologies form smooth surfaces. This is a basic hypothesis I use. And having this hypothesis true, We can address these problems using very well-developed, universal and robust field of Riemann optimization methods that are generalization of standard gradient optimization methods on multidimensional smooth surfaces. So here is a research plan that I followed in order to develop tool for optimization problems, general tool for optimization problems in quantum technologies. First of all, one needs to prove the hypothesis I introduced in the previous slide, i.e. that the typical constraints emerging with optimization problems of quantum technologies are smooth surfaces. This is a mathematical problem that I have proven. Then, having this hypothesis true, one needs to derive some Riemannian geometry routine for all types of quantum constraints. On the next step, one needs to build a library for this purpose, built on top of some deep learning library. In this particular case, I have chosen TensorFlow because of some reasons. And this library should provide generalization optimization methods on constraints that emerge in quantum technologies. Then one needs to test the library in typical optimization problems of quantum technologies, including design, control, and model identification problem. And two last steps are write a documentation on the library and prepare research papers. So here I measure our solution in terms of key success factors that are universality, the most important one, mathematical guarantees of convergence, scalability, and efficiency in practice. One can see that in comparison with already existed methods, our method is quite scalable, quite efficient in practice, but what is the most important is that it is very universal, that allows us to address some new problems that have not been addressed before by our solution. So this is the first part. This was the first part of my project. Now let me turn to the second part of my project that is dedicated to model identification methods. So before diving deeper into methodology, I need to introduce two important concepts. Concept of non-Markovian dynamics and Markovian dynamics. So what is a non-Markovian dynamics? Assume that we have some dynamical system like human here. And this dynamical system evolves somehow in time. And at each particular step, before doing the next step, this system looks back on its prehistory, how it behaves before, and then looking on this prehistory, let's say looking on k previous time steps of its dynamics, it decides what to do the next. So it behaves like a human who makes decisions according all his previous life. So its behavior is quite complicated, like a clever behavior. And non-Markovian dynamics is like a human behavior. So Markovian dynamics is a vice versa situation. We have a system that doesn't remember anything about its behavior, its previous behavior, about its prehistory. It doesn't rely on the previous experience, and it behaves in a very simple way. So this system behaves like a goldfish that doesn't have memory at all. So these two concepts are introduced, and it turns out that in real physical experiments, quantum systems behaves like a human. They have a non-Markovian, they experiences dynamics with memory. The reason of that is that quantum system interacts with the environment, and environment takes a role of the memory. It turns out that if we want to build a model of dynamics of the system, experience memory effects is a difficult problem because behavior is quite complicated. We can try to build the model based on data, identify model of the whole system, including environment and quantum system. But it is an extremely complicated task because the state of whole system, including environment and our quantum system, is extremely high dimensional and hardly can be simulated on classical computer. Moreover, in usual experiment, physicist doesn't have an access to environment. He cannot measure state of environment. He cannot identify model of the environment. So this problem is also complicated. One of the possible solution is to reduce complexity of this task, and instead of a high dimensional full environment of the quantum system, we can consider effective low dimensional environment, low dimensional small memory that leads to the same dynamics of the quantum system. This trick is called Markovian embedding. And in this case, now we can consider dynamics of the whole system that includes target quantum system and low dimensional memory. In this case, dynamics of the whole efficient model is memoryless and low dimensional. And again, in this step, I need to introduce a hypothesis that it is possible to reconstruct this type of model, Markovian embedding, only from information about the system. We still don't have access to the environment. So let us skip this slide. Here is a research plan that I followed in order to resolve this problem. First of all, one needs to prove the hypothesis that it is enough to have information about a system in order to reconstruct effective model of the environment. The next step is to design the appropriate method for the embedding reconstruction, combining tools from the field of applied math. Actually, we found the probably the best one, that is combination of engineering tool that is called dynamic mode decomposition with special data preprocessing. And two last steps include write the code, test the method on typical examples of non-Markovian dynamics, and prepare research papers. On this slide, you can see the comparison of our solution with all previously developed ones. In terms of all key success factors, our solution is a state of the art. We have proven it, not yet published, but we have proven it. And it seems that it is one of the best solutions for model identification in quantum technologies. It is also very well compatible with the previous part dedicated to optimization in quantum technologies. And overall, these two methods form some kind of answer on the given research question. That's it. Thank you for your attention. If you have any questions, I would be glad to answer them.
Thank you very much. Any questions? Well, maybe I can start, Ilya. You seem to have two separate projects here, two separate objectives. Am I seeing it right? Because
yes, but yes. Sorry.
But how do they relate?
Actually, they are related to each other directly. First of all, let's have a look on the first part. First part is a very general tool that can be used to address control, that can be used to design control methods, design methods, and also model identification methods. But we found that a particular technique can be much more reliable for model identification methods. It is like a T-shaped project, as Anastasia said last time. We have a very general tool for all the problems, and we also added like a very high performance one that a bit more narrow, more specific, but has very high performance. So they are very well linked and dedicated to the same general problem: design, control, and model identification in quantum technologies.
Okay. And when you say mathematical guarantees there,
yeah,
you're talking specifically about convergence or more general?
More general in this case, because usually we have the statement that either method converges to the global minima or not. But here we can think more broadly. We have sometimes we have guarantees of global convergence. For example, for the second our method, we have these guarantees. Sometimes we have guarantees of convergence to saddle point. That is not enough usually to design a completely reliable tool, but already good for some practical purposes. So all the field of deep learning actually relies on convergence to saddle points, to local minimas. And we have completely heuristic methods that we cannot predict how it behaves, like genetic algorithm or simulated annealing or something else that are sometime they work quite well in some applications, but sometimes they don't. And in general, we cannot prove even convergence to local optimals. So we have some kind of three levels of guarantees.
Okay.
No guarantees, local convergence and global convergence. So my first part, method at the second level, we have guarantees of local convergence. And the second part at the top level, we have guarantees of global convergence.
Okay. Good. Okay, thank you very much. Any questions from?
I would like to thank you, Ilya, for your presentation. This time it was much clearer what you are doing, and yeah, really thank you. After the long discussion we had previous class. I have a simple question. Can you provide any examples of these quantum systems, quantum devices, which you are developing your methods for?
Yes, I can. So basically, in any experiment with quantum systems, we usually deal with open quantum systems. Some examples, even in Russia, for example, in Russian Quantum Center, experimentalists develop different platforms for quantum computing based, for example, on cold ions. So they have a cavity, vacuum cavity, with a specially designed potential trap where they place ions, cold ions. And these ions have some quantum levels that can be controlled by external laser field. Yeah. However, these ions interact with surrounding media, for example, with vacuum electromagnetic fluctuations that introduces all these effects like dissipation, memory, and so on. And in order to be able to robustly predict dynamics of such a systems, we need methods for model identification. We can measure this system, process measurement data, build a model, and then predict dynamics of such a systems using data-driven model, and then control as well. So this second part directly can be applied, for example, to this kind of systems. The first part, for example, currently I'm solving very practical, not me, but some students is solving a very practical problem dedicated to identification of bad quantum gates in quantum programming. This is an optimization task that can be resolved by this library, QGOpt, and we already have some results. And it is very practical because let us assume that in 1 year we would have a platform with several qubits that can be used to address some applied mathematical problems. But something goes wrong with your system, with your hardware, and some gates start to work improperly. Then you have to identify each particular, what is the gate that works improperly in order to fix this problem. So it is some kind of a monitoring system. This is another application. So I can continue, but I think that it is not relevant directly to the topic of this discussion. So at least we have these two examples.
Thank you, that's cool. Maybe just when next time you have a chance to present for more like general audience, just include one slide in the very beginning with these examples.
Okay.
The
Okay,
context,
I'll
yeah.
do it.
Totally cool.
Yeah. I agree that your reference model is much clearer and yeah, great progress there. That's for sure.
So I haven't included links here because it is already quite overloaded, but I can do it if it is necessary. So basically here, there is no any assumption actually for each link. For each arrow, I can suggest some publication, some
Okay.
experiment, and so on.
Good. That'd be good. Okay. All right. Okay. Good point. Any other questions? No? Everybody, no questions for Ilya? I'm sure there are some.
Well, may I ask a question?
Of course.
So, Ilya, when you started this project, what was the gap in the existing situation and what was your motivation to start it?
Okay, the gap is very clear actually, because when I started, there weren't any general tool for optimization in quantum technologies. Some particular cases were solved with mathematical guarantee, but there were many problems that are like too complicated, like in deep learning, that couldn't be solved by standard techniques. And then I decided, why not to use the approach like in the deep learning? We have we can design arbitrary loss function that is non-convex. There is no guarantees, but in practice, deep learning usually works quite well. Why not to consider the problem like complicated quantum setups that we want to optimize as deep learning task? The only tool that is needed to do this is to generalize optimization methods from deep learning on curved surfaces, multi-dimensional surfaces. And this is what I've done. And this is enough to address huge variety of problems. This was my motivation. Actually, there weren't any such kind of tool, and I decided to make one.
Good.
Is it clear?
Yes.
Yeah, okay. Very good. Anything else? Okay, let's thank you very much, Ilya. I think you're looking forward to see your final proposal. I think yeah, I like your reference and it's clear. My only comment is that link, because when you started the second part, you started with an hypothesis which appeared to me to be
Yes.
to be disconnected from the first. You just need to make a link somewhere. When the way you answered was very good, by the way.
Okay, thank you. I'll do it.
Okay, good. All right, very good. Let's go to Dennis then.
So, can you see my screen? Is it okay?
Yes, we can.
Okay, so good afternoon, dear colleagues. My name is Denis Shepakov. I'm the third year PhD student of engineering systems. And my research is devoted to the development of control system for the continuous casting process. The continuous casting process is the first and the main stage of the modern steel making process. So here you can see the scheme for the continuous casting machine. Molten steel is poured from the ladle to the tun dish and then is distributed between several molds. The mold provides the primary cooling of liquid steel, which results in formation of solidifying shell. Then the ingot passes the secondary cooling zone with water sprays, moving by the roll supports, and finally solidifies. And then in the end, the slab is cut off in the cutting zone. Further, the slab moves to the stock where it cools down and awaits for the further processing. Then the slab is reheated in the furnace before further processing, for example, before hot rolling. And finally, we get the final product in the form of steel sheets or steel rolls. During the casting process, various defects may emerge, and the complete list of defects includes about 450 items, but the most common of them are the centerline segregation, when the alloying components, such as, for example, manganese, are moved towards the center line of the ingot during the solidification, which causes axial fragility of an ingot. The porosity, where the vacuum pores are formed inside the ingot. So here you can see the section of it. And the most frequent type of defects on which I'm focusing currently is the internal and external cracks. And nowadays, each plant has its own control system powered by various numerical models to control the casting process and minimize the defects. However, the majority of the systems are adjusted manually once the system is installed for the particular casting machine. And despite the variety of all of these industrial solutions, the number of load products as of last year reached 0.35%, even for the leading Russian plants such as Novolipetsk Steel, Magnitogorsk Iron Steel Works, and Severstal, which led to losses of billions of rubles. So it's obvious that there is a gap somewhere in the situation which does not allow to control the casting process perfectly. So, and the goal of my research is to design such a system, such a control system, to forecast and prevent flaws in casted ingots. And the research question here is how to predict the emergence of cracks in casted ingots and to exercise the necessary mitigation actions. And my hypothesis is that the emergence of cracks can be predicted by computation of a so-called damage accumulation parameter during coupled analysis. So I'll focus on this a bit later. And my contribution here is that I'm going to develop a new complex multi-physical model for the control system, and I'm going to collect all the best parts of all the existing control systems and design my own. Well, now we're heading on to the methodology, and I'll move step by step here. So each of the blocks for me corresponds to the 1 year of PhD study. So the first step for me was the research clarification, when I reviewed the literature on existing models of the continuous process and the literature on existing slab defects prediction criteria. So, and the results of the research clarification is presented here in form of a reference model. So here I included the main references which I constantly use during my research. So I identified the key factor is the intensity of water flow in the secondary cooling zone. And the intensity of water flow increases the rate of solidification of an ingot, and according to the literature sources, the rate of solidification increases the amount of the damage accumulation, which causes cracks. However, at the same time, the rate of solidification, when increases, decreases the segregation of alloying components at the same time. So obviously the number of cracks and the amount of segregation decreases the final quality of a slab and the quality of final products respective. So here we must somehow find the optimal intensity to minimize the cracks and to minimize the segregation at the same time. And there are also other defects which affect the quality of a slab, which are outside the scope of my research. And the measurable success factor for me is the amount of flowed product, which we get finally. So the next step is the descriptive study part 1. For me, it's comprehensive. So during the first and the second year also, now I'm constantly communicating with the different engineers from Russian plants. And I constantly analyze the industrial historical data on slab defects and corresponding custom parameters. So our team receives this data directly from different Russian plants. For example, we are working with data from Novolipetsk Steel, from Severstal, and with Evraz, and we are trying to find the correlation between the data on temperatures and on different parameters of the casting mode, such as ingot velocity and many others. And we're trying to find the correlation between these parameters and the amount of ingot defects, especially the cracks. And after analyzing all of this, I'm heading on to the impact model. Here I identified the secondary key factor, which is the completeness of this historical data, which we obtain from the plant, because it directly affects the accuracy of model validation. Of course, the accuracy of model validation affects the accuracy of the final numerical model for each particular casting machine. We also may vary, for example, the size of mesh for the finite difference solver, which I'll focus on later, which will increase the time of computation. And at the same time, yes, by increasing the accuracy of numerical model, we decrease the quality of the control system because the time of computation increases and the control system must operate in real time. And the quality of the control system, of course, affects the quality of the secondary cooling. And there are also other factors which may affect the quality of secondary cooling that we cannot predict. So they are random. For example, the destruction of rolls or nozzles in the secondary cooling zone. Well, the third step for me which I'm on now is the prescriptive study. So for me, it's comprehensive. It includes the development and validation of the numerical model of the casting machine and the development of their control system for the continuous casting process. And now I would like to give you some details about the numerical model. So the numerical model implements the coupled analysis of an ingot. So it consists of two parts. And the first is a transient thermal analysis, which is based on the Fourier-Kirchhoff heat transfer equation. So in my case, to make the model operate in real time, I consider only the two-dimensional section of the ingot, which is normal to the casting direction. So we can use this assumption because due to the scaling factor, due to the ingot dimensions, the temperature gradient in the casting direction is much less than the temperature gradient in cross-section. So, and the next part is the nonlinear structural analysis. So here we use the assumption that all of the strains are normal to the section, which I mentioned on the previous slide. However, we consider all of the components of the strain, which are elastic, thermal, and creep strain. And now I'd like to give some details about the damage accumulation parameter. So I would like to keep it simple. So the idea is that for each particular type of steel, we carry out several experiments when we take the round specimen and we carry out some tension compression tests. So during these tests, we measure the critical strain at which it fails for each particular stress and temperature. We measure the strain rate and we measure the time of failure. In other words, when the specimen fails for the specified stress and the temperature. And then we can compute the damage accumulation for each element of the section with this formula, integrating this elementary damage from the moment of solidification to the current time. And if damage accumulation reaches 1, the element is considered as failed. So the crack appears. So, and the final stage, which is the way forward for me, is the verification of the control system on a test stand or on the real equipment. So the last slide is devoted to the model validation. So as the model is multi-physical, it includes several dependencies with undetermined coefficients. And the most important dependency is the Nozaki formula, which includes 3 unknown coefficients, C1, C2, and C3. And this formula represents the dependency of the water steel heat transfer coefficient in the secondary cooling zone, on water flow. And to determine these coefficients, we use the historical data that we obtained from the plant earlier. So we construct the objective function. So here, f is the objective function, which depends on the unknown parameters for this formula. The Ti and Ly are the temperatures and the front lengths that we obtain from the historical data that we receive from the plants, and the T and L, depending on C, are the parameters that our model computes. And our goal is to minimize this function. And as we obtain the minimum of this function, the model is considered valid. So in conclusion, I would say that the 2 stages were completed, the third is in progress, and the fourth is a way forward for me. So thank you for your attention. I'm ready to answer questions.
Thank you. Thank you, Dennis. Any questions?
Thank you, Denis, for interesting. So who is the first?
Victor, you can continue if you want. I will ask my question later.
Thank you, Denis. Please go to the slide number 9. So you told this assumption. This is the assumption, but I thought it was kind of proven fact. Probably you have proved it. Where have you make this assumption from? Is this follows from the historical data? This like temperature gradient in Z direction is much less than XY direction. Does it follows from historical data, or why have you picked this assumption?
I understood it. So we have 2 reasons. The first is that it's quite obvious that the dimension of the cross-section, which is, for example, 0.25 meters on maximum 2.5 meters, is much less than the total length of the ingot. So thus, the ingot will solidify slower in Z direction than in cross-section. So the solidification front will move much slower. It's the first part. And the second part, of course, during my research, I've already received this question. So especially for this, I carried out another research I carried out another computation where I considered the complete 3-dimensional ingot, and the results were very similar to each other. So the accuracy of this method is approximately 95%. Comparing to the 3-dimensional scheme, the accuracy of the 2-dimensional scheme is about 95%, comparing to the 3-dimensional scheme.
Cool, thank you.
Denis, may I ask a question? What is QV in this? Is it external source of heat? Am I right?
QV is the internal heat.
Oh, internal.
Internal, yes. QV is the internal heat. So for this situation, it's the heat from the solidification process between solid phase and liquid phase.
I see. This is the amount of heat that sample observes while phase transition. Am I right?
Yes, yes. That's
okay.
This from phase transition. Yes.
Okay. So, but it seems that this equation is linear. Standard heat equation is linear. Why do you need to use some complicated methods? So you can use simple Fourier transform, let's say, and
no. Here we must compute. So here we have, first of all, the varying boundary conditions. So first of all, we have the mold, then the air, the rolls, and the nozzles. And we have to solve this differential equation, or the second order differential equation for this section. And the most common method for this is just use the finite difference scheme, which I am using here. With the explicit finite, I use the explicit finite difference scheme to solve this equation.
But this is a linear problem. It can be formulated in terms of eigenvalue problem of the differential operator on the right side. So you can find simply eigenfunctions, and then you can use Fourier method. You don't need to use some discrete in time scheme and so on. What is the objective? Is there any other equation that is nonlinear and more complicated than this, or you solve only this, or you are solving currently only this equation?
Well, it's a good question. Unfortunately, I'm not so well at maths on what you have just said, but I assume that this is not possible in my case because the casting conditions, such as, for example, the velocity of the ingots, the water flow, they are varying in each time, each particular moment of time.
So rho c is a function of time, you mean, and QB
yes,
also is a function of time.
I think it will be very complicated to calculate for the eigenvalues and the Fourier coefficients for this. I think that it will that the computation time in this case will be much higher than when I use just a simple finite difference scheme.
Okay. Could you please go to the optimization part where you optimize some function? So this is objective function, right? But
yes,
with respect to what set of parameters you optimize this function? Well, what is the parameter?
Yes, just an example. I showed here the Nozaki formula. This formula is unique. The coefficients of this formula, C1, C2, and C3, are unique for each particular casting machines. So they are determined for each casting machine respectively. So each time when we will implement our control system on a plant, we will have to validate the model based on historical data. For example, just an example. Temperatures in certain points of the ingot that we measure with help of pyrometers and the front length, for example. So this set of parameters is used in this Nozaki formula, which represents the dependency of the heat transfer coefficient for the boundary conditions and the physical water flow in nozzles.
And you perform optimization over these parameters.
Yes.
So you try to find best set of parameters. Okay.
Yes. But it is not the only set of parameters. So the set of other parameters, I can introduce other parameters if these three are not enough for me.
No, I just the question. So why I'm asking this question is that you said about optimization problem, but didn't introduce set of parameters, constraints, just only the function. And then I ask the question, what is the parameters, what is the constraints and so on, but it's okay. I see now.
Well, no, I may answer that the set of constraints is just can be obtained from the, previous experimental data. For example, we know that C3 must be less than 0.01, that C1 must be between 1,000 and 10,000, and etc. So the constraints are also involved in the optimization problem.
Okay, and very last question: what is the method that you use? What is the optimization method that you use?
Well, it's a good question because I programmed myself an LDOMIT algorithm. I tried to find the minimum with help of this, but I didn't succeed in finding the global minimum with help of LDOMIT. So now I'm now working on more accurate global optimization algorithms. I would like to try the Bayesian optimization, for example. So, like that.
So again, very last question. If I remember it correctly, NerdLMeet is a zero-order optimization method, so it doesn't involve gradient information. Am I right?
Yes, yes. So that's why I chose it, because it's very simple.
But it is so zero optimization. People usually use zero-order optimization methods when they don't have an access to gradient. So do you have an access to gradient here, or?
No, I don't. No, I don't have an access to gradient here. I can't calculate the gradient. Well, actually, I didn't try it but I assume that it will be non-continuous function. So,
But anyway, I think you should try it, because with zeroth order methods like Nelder-Mead or Bayesian optimization, I don't think that you will find a good minima. I think first order optimization methods, if it is large scale problem, will help you definitely. Probably
Well,
second order, but I'm not sure about convexity of your function, but I think you need to just a recommendation.
well,
Try to use.
I will try. Well, maybe it's possible. So I made an assumption that it's not. So I'll try.
But
I'll
then
try.
I don't know, but I think it's a very well-behaved physical phenomena. So I think you should be able to estimate the gradient. I would say.
Well,
And
actually,
Denise,
maybe.
as a big fan of automatic differentiation, you can use, let's say, JAX or PyTorch in order to calculate gradients with almost zero efforts. So I think it will help you definitely. It should help you. Just,
Okay, it may be,
just my
but
recommendation.
Yeah, you should continue to exchange on this. Very good. Thank you, Ilya. Dennis, I have a few questions. So I think your research question hypothesis are very clear. My question is, maybe if you can give us, what is the time of solidification? What is the time constant of the solidification process? How long does it take from the start of the process to the solid ingot?
well, the common for the size of the ingot that I presented, it's 0.25 meters on 2.5 meters.
Yeah.
The common velocity of an ingot is 1 meter per minute, and for this velocity, the solidification length is 16 meters. So the solidification time respectively is 16 minutes.
Okay.
Full solidification time is about 16 minutes, from 16 to 20 minutes.
Okay, okay, good. Well, I know it's a very critical and very difficult process to control. There's no doubt about it. Can you predict segregation? Probably not, right?
No, it's very complicated task, because we have to maintain the growth of dendrites. Actually, I tried to model it, but it's not possible to model the growth of dendrites coupled with this thermal problem, because the size of mesh is very different. For example, for this thermal problem, the size of mesh is about 1 millimeter, and for the growth of dendrites, it's less than 1 micrometer. So we cannot solve these problems simultaneously.
Okay, very good. Go back to your reference model, because I just want to make sure I understand the control problem. No, the impact model. What I understand from your impact model is that you don't control the initial intensity of the water flow, right?
No, I control the intensity of water flow. So I tried somehow to show it with this dashed line. So,
but then what do you call secondary cooling and primary? If there is a secondary cooling, there must be primary. I understood that the intensity of water flow at the bottom is your primary cooling, and you have secondary cooling. Is that?
oh, no, sorry. Maybe it's my mistake, and I didn't mention it, but I'll show it here. In terms of continuous casting, the primary coolant is the coolant in mold, and we can't control it. We can't control the water flow in mold. It's always constant, but we can control the water flow in the so-called secondary cooling zone.
Okay.
Yes. So by secondary cooling, I mean the secondary cooling zone with the water sprays, where we actually control the water flow.
Okay, so in your reference model, the impact model, that should be quality of secondary cooling, but you need to make a link here between water flow and cooling somehow. I would put quality of secondary water flow, or I don't know how you would call it here, but you need to, I saw the line, I didn't know you should have an identification of this line. So you're controlling, but can you control, well, what can you control? The volume, how many variables do you have on this control system?
I can control the water flow in any segment of the casting machine.
Okay.
It's very much for me, yes.
And the volume, you can control the volume and the temperature? No, the temperature of the volume, right?
The temperature is the output factor of the volume.
The volume of fluid, the flow level. You
Flow,
can
yes, the
out
flow.
segment.
The volume, yes, the volume per unit of time. Yes, so liter per
Okay.
minute. Yes, that's the
That's my only comment on your diagram, which is very good because you put the references and you have the all the information there. It's just this that I see it from your diagram. You just need to make sure that there is that it's easily understood there. Okay,
okay.
very good. Any other questions? No, no other questions?
Sorry, may I comment? So probably I haven't seen. Where is your system in this impact model? So you propose the solution, and where is it on this diagram?
So the system itself is not mentioned, but the quality of the system is mentioned. The quality of the system and the system, the control system is powered by the numerical model, and then accuracy of a numerical model is also mentioned here. So I may say that all of this, all the left part of the impact model is my control system or its components.
Well, I think that you probably should make it into, you should have a lozenge, right? An hexagon rather, as a symbol. If we want to follow, I think you should follow. I think that I would have an hexagon and then you could point at your quality of control system, or it's probably the quality of control system that would be your hexagon.
Yes, maybe yes, it would be better to draw it like this.
Yeah, yeah.
So
yeah.
this is the main support method.
Yeah, which influences your quality of secondary cooling, which or accuracy of numerical model. Yeah, we would feed into this, but probably your completeness of historical data could go directly into your model, right?
Well, maybe yes, but between the historical data, the model, there is model validation, which also affects the accuracy. So I don't know.
Okay, so have a look at it. Okay, any other questions?
Just minor comment, Genius. I believe in your hypothesis, you mentioned coupled analysis. And actually, I was questioning myself, was this till the slide with this coupled analysis? So maybe you can just structure.
The coupled analysis means that we carry out two analyses simultaneously. So in my case, is the thermal and the structural analysis. So we compute temperatures, and after this, on the same step of the solver, we compute the stresses and strains.
And this is that.
Strain.
The point is that you use this term like in the most beginning, like in the hypothesis definition, and only at this slide you elaborated, you explain what's this. So it was a bit confusing for me, but it's fine.
And the equations for your nonlinear structural analysis, you're doing finite element analysis on it?
Yes, so here I'm implementing the finite element analysis.
Okay. In the 2D cross section.
Yes.
Okay. Did you try to do a limited thickness? Would there be any value? Yeah, you know, I understand that, but you didn't think you did. Did you try to do a limited thickness, or to do an average over a certain thickness of material? Would that be, because the cracks, I would imagine, are going to develop on the length. That's why I was wondering.
Well, there is a trick, because there are several types of cracks. So there are transverse cracks and longitudinal cracks. So they may be normal to the section, or they may be parallel to the section of the ingot. So there are different. And the criteria for these cracks are different. So, for example, so this scheme that I introduced here, so is used. So there is so this scheme is one-dimensional, and it is used for the transverse cracks. And the second scheme that I didn't introduce in this presentation, but I'm also using that you mentioned is the two-dimensional finite element scheme, where I consider this cross-section. So, and this scheme is used to predict the longitudinal cracks. So, because it's more accurate.
Okay. Any other questions, guys?
I have a small question. Denis, can you please open a slide with losses which manufacturers carry because of the problem? In the very beginning. Yeah. In what period are these losses you mean? Is it in here, losses 2 million rubles in here, yes?
Yes, every year. Not 2 million, but 2 billion rubles.
2 billion. Okay, thanks. Yeah, it's just to understand amount.
Yeah.
To be honest, for these plants, for these leading Russian plants, it's not too much. So 2 billion rubles, it's very low. But for example, for the plants which are low in this list, that may be very, the amount of low may be higher. This is maybe 2 or 3%. So.
And Dennis, you don't mention the research gap. You focus on the industrial problem. You cite some, you refer to some research papers, but then you don't mention the gap that is in the research side. We see the problem, the industrial problem with cracks and losses and so on, but can you find anything literature review wise that would indicate what is published? And maybe there's lots that's not published on this. I wouldn't be surprised. Did you find anything there?
Well, there is one big problem with this, which affects the accuracy of the numerical model, which affects the control process. And this one big problem is that the high temperature processes in steel are very hard to model and predict. They may be stochastic, and sometimes it's not possible to compute the process at all. So that's the big problem. And to be honest, it's very hard to solve it, if not impossible, I may say.
Okay. But then in the literature, how many papers have been published? I would imagine that goes back 30, 40 years ago, right?
Maybe even 60 years.
Okay. But how many papers have been published on this specific continuous casting of steel? And I've seen it applied in Canada to aluminum, maybe 15, 20 years ago. But how do you, how many papers in the last 5 years on this steel, continuous steel casting?
Well, I noticed that for the last, for example, 5 or even 10 or 15 years, the number of publications decreased since comparing to the maybe 20 or 30 years ago. So the majority of publications which I use as a literature sources, they were published more than 15 years ago. So
Okay.
yes, nowadays not so many papers are published.
Okay. But does that mean that the North American...
The researchers came to some kind of a limit, maybe.
Yeah, okay. All right. Would publication on aluminum be useful? Probably not, right? It's very different behavior.
I don't know.
Okay.
Maybe yes.
Okay.
All right. Thank you very much. Anything else?
May I add, please, on this topic, that we can look on this question from an entrepreneurial point of view, how Denise just mentioned that maybe this loss is not so much for mentioned plants, and how do they solve this problem right now? Maybe change a system or change approach, and for example, buy your system when you finish it will be too difficult for them, too expensive for them. You can face with problems that they don't want to change this, to solve this problem in another way. Have you thought about this previously? I assume that you have direct question from plants to solve this. Yes. Do you understand my point?
Yes, I'll answer it. Actually, I'm sure that the control system as such will not be implemented. However, there is a point here. The numerical model for this control system that I developed is applicable for other problems. For example, at the moment, I'm working with the Yevraz plant in Novokuznetsk. So they asked our team to calculate the ingot shrinkage and to get the final length and the final mass of the slab which they are cutting. So, and this model can calculate not only cracks, but I made several changes in it, and now I can calculate the shrinkage. So the control system itself is not very applicable. However, the numerical model can be adjusted to solve various industrial tasks, not only predict the defects.
And why do you think the control system is not applicable?
Because from the engineering point of view, when the plant buys themselves a new casting machine, it already comes with a control system.
Yeah.
So that's the very problem here. So I think the main point of my research is to design the flexible numerical model, which can be adjusted for various industrial tasks, not only for the control system, for the particular control systems.
Okay, good.
I'm sorry, may I ask the very last one?
Yes,
Okay.
the very last idea.
Okay, then we can skip it. If you don't have time, we can skip it.
Go.
That's Denise, as I understand you correctly, your goal is to make such a control to adjust parameters in such a way that the gradient of temperature in the sample varies not too fast. Am I right?
Not too fast and not too slow.
I mean, it should be restricted, and you have.
My task is to find some optimal cooling mode, some optimal water flow.
Yeah, this is what I said, that you have some control parameters, and you want to adjust these control parameters in order to make the solution of your heat equation gradient of temperature to be in between of some boundaries. Am I right?
Yes, but what you're talking about is the purpose of the model validation. However, once the model is validated, my goal is to go further and to vary the cooling mode, the water flow, to minimize the damage accumulation in my case, to minimize the amount of cracks.
Yes, but damage accumulation is probably
the criteria which allows us to predict the cracks.
Yeah. I mean that the gradient of your temperature gradient is the direct cause of damage of your sample. Am I right?
Yes, you are totally right.
So you are just gradient. You're just gradient of the gradient. Actually,
yes.
You have linear equation. You have gradient of the gradient, and you want to restrict it in some region. And it seems to be a.
Well, I think it's not that. I see your point, but I guess it's not that easy. Well, I'll try to implement what you told me earlier. So thanks for your comments. I'll try to implement it, but I assume that it's not that easy as you see it.
Okay.
I have a question. One last question, Dennis. From what you answered earlier to the question, one of the question you said, well, it's not the control system that I want to improve. It's really the simulation. Shouldn't you reformulate your research question at that level?
Actually, now I'm working on it.
Okay.
I haven't changed yet, but actually now I'm working on it. So
Yeah, so raising, raising the research question, because at a higher level, and
Yes.
okay.
Because
good.
actually, Professor, as you remember, I started with the digital twin of the complete process, starting from the casting, finishing with the furnace. Now I narrowed it down only to the casting machine, and now I think I'll narrow it down only to the casting process. So not the
Numerical model. Yeah, I remember. Yes, you're right. Okay, good. All right. So that's it. Thank you, Dennis. Good work. I like your research question and hypothesis, and your clarity was very good. Thank you. Okay, so Anastasia, next. So everybody has to work on the evaluations, and this Thursday, who's presenting this Thursday? Ibrahim,
Give me a second.
Nadezhda.
Yep, that's Nadezhda, Victor, Mikhail, and Ibrahim.
So we have 4. Okay, so Victor, Ibrahim, and who's the last one? Nadezhda, right? Nadezhda, Ibrahim, Victor, and Michal. Is that it? Okay. All right, so we'll have to be efficient, but I think we can manage. We were a little slow with Yuri. It took us a little time, but can happen anytime. It was the first one. So thank you very much for the presentation. Very interesting. I think I see that you are mastering the concept of research questions and hypothesis, and getting the plan more and more. So I think we'll refine as we go here week to week as a presentation. You'll arrive at a very refined model. So let's see. All right. Thank you very much, all. See you Thursday.
Thank you.
Bye-bye.
Ciao.
Thank you. Goodbye.
The evaluation forms, we have to send it to email or to your email, or?
I would provide a place to submit those
Okay.
on Canvas.
Thank you.
Thank you.